4.10 Probability Plots. In many practical applications, we are collecting data to study a phenomenon. That data can be thought as a random sample from some population. In many cases, it's important to determine the probability distribution that approximately describes the population. More often than not, the only way to determine an appropriate distribution is to examine the sample to find the probability distribution that fits. There is a tool that is called the quantile plot. So, if a set of observations is approximately normally distributed, a normal quantile or QQ plot of observations will result in an appropriate straight line. So a QQ plot is a plot in which the theoretical quantiles are compared with the sample quantiles, and if our sample that is shown here as these dots are on a straight line, means that there is a correlation in between the sample quantiles and the theoretical quantiles. A good video to see the full explanation of the quantile plots is given in this link, and I will put it on Blackboard for you to explore. Let's suppose that we have this data from a sample of some phenomena. So this is a sample. We collect the data and is ordered also from the smaller to the higher value. And so from this we have 1, 2, 3, 4, 5, n is equal to 5. And we want to compare with this normal distributed function. And this is the standard normal distribution, meaning the mean is 0 and sigma is equal to 1. And then the total area is equal to 1. So if this data from our sample is correlated with this normal distribution, that will correspond to a distribution in the plot. So for n equal to 5, we are going to divide the area into 6 different regions. So the total area divided by the number of regions is equal to 1 divided by 6. We have to add 1 so we can have 5 different points. So this is equal to 0.166, and then let me do it in the plot. So we are going to have this. So with this, what I'm expecting is I'm dividing in equal area. So this is 1/6, this is 1/6, this is 1/6, this is 1/6, and this is 1/6, the tails. So it should be, as this is taller than this part, so the base should be increasing and increasing every time. So we have 6 different areas, 1, 2, 3, 4, 5, 6. That corresponds to 5 different points, 1, 2, 3, 4, 5. So as they are equally distributed, so we can find the quantiles corresponding to 1, 6, 2, 6, 3, 4, 5, and 6, 6. Well, 5, 6 will be the last one. Okay, now what we are going to plot is the result of those quantiles and compare them with our sample. So in our plot, QQ plot, what we do is that we have the theoretical quantiles, and in the y-axis, so we have the sample points, the sample values. So the points that we plot 1 to 1, if they are in agreement with a line, means that this distribution follows a normal distribution. This is an example. In this case, we have data that came from the production of 255 gas wells, and we can see that in this case it doesn't really match, like compared with the straight line, and it's because the underlying distribution is not normal but log normal. So if we apply the natural log, so we have, and if this is y, and we apply the natural log of y, and we plot it again, so this is going to be normally distributed. So in that way, if we are comparing with the normal distribution the data, we can tell that is log normally distributed. So next I'm going to show you some example in Python, and I will publish the worksheet in Python so you can play with it. This is an example generated with Python. This is an IPython or Jupyter notebook, and I'm going to show you how do you plot quantile plot using Python, which I think is the best way of doing it and not by hand. So I'm going to start this little slideshow with from within IPython notebook. So let's suppose that we have some data, and in this case I have just a small set of data, and it's the same one that I use in the lecture. Well, first of all, I have this command to reset the variables that we have in memory. So to reset the variable's state is very wise every now and again, so you know what you have in memory. I'm loading some libraries, NumPy as NP, that's the linear algebra and numerical library. Stat models, it will provide me the function that I'm going to use, and I'm going to include the stats models as SM, and the matplotlib pyplot to plot the data. So what I'm creating here is an array, a NumPy array in fact, with the data that we have. So I input the data this way, and this command will give me the length of the data if I need it in any case. So I just shift enter, and if the cell will run. So the length is 9. Okay, once we have the data storage in an array, it's very easy to do the qplot. So as I told you, it's in the SM library, the statistical models library, and it's called qplot. So we just input q. I'm going to tell, that's the only thing that you have to do, but it will be quite just the points. But if I put these 2-second variables, feet equal true and line equal 45, it will compare visually with the line, and it will feed the data into the standard data. And the next command is just to show the plot. So let's go, execute it. So we have our 9 points, 1, 2, 3, 4, 5, 6, 7, 8, 9, and on the horizontal axis we have the theoretical quantiles, and in the vertical we have the sample quantiles. We don't have to compute the quantiles or anything like that, so it's very nice. It just does everything for us. So we can see here, for example, this data is very much on a straight line. So depending on how is our data, we can decide, well, in this case, we can assume this is a normal distribution or came from a normal distribution. Okay, so that's it. That's as simple as that. That's the way that you use IPython or Python to verify if your data is normally distributed. But let's do some extra experiments. And to do that, I will generate data with the computer. And it's very easy. So what we have is in NumPython has the capability to create random data. And what I'm telling here in the first line is like telling NumPy, okay, create some random data that is normally distributed, and mu is equal to 3, and the standard deviation is equal to 1, and I want 1,000 points. Okay, well, this is a line that we don't need it because we already import the library, so let me delete it. And I want to plot the data. I want to make a histogram, and I want of the data that we just produced, and I want 50 bins, so 50 columns of data. So this is the data. We can see that is, in fact, it resembles a bell, and it's symmetric. So if I change, and the mean is about 3. Okay, if I change the mean, it would produce a different data. Let's say, for example, 5. We can see that the mean is around 5. It will produce 1,000 elements. And the standard deviation, let's say now the standard deviation is 10. So now the range, we should have compared, the range is different, is between 0 and 30, well, in between 5 to 30. So let's say now back to 1, so we can have a comparison. See, the data is between 5, the mean is 5 to 8. So yeah, that works. It produces some random data in the way that we need to use it. So with that data, we know that it was produced as normal distribution. We can use it to the function qqplot to test. So I'm generating here. Let's change a little bit. Let's change the standard deviation, not the mean, to some other value like -5 and 3. And I'm plotting just 100 points, and then I'm using that data to plot it with qqplot to see if it fits. It should fit. Yeah, it does fit. So if I increase the data, it will just increase the number of points. Yeah. So that's a way of testing with some computer generated data. So now we were producing some normal distributed data, but now what if the data is log normal? How we will see our data in our qqplot? Let me first of all, I'm going to comment this line, and I'm going to plot this log normal. The only thing, no, right now it's fine. So we can see that this is not on a line. And if I keep changing, like for example, to 1,000 points and 5 and 10, so any log normal, look in this case, is not producing any straight line. Now, we know that if something is log normal, if we apply the logarithm of our data, it will be normally distributed. So let's do it. So in this line that is commented, I just computing the logarithm of our data, and I'm calling our function again. Let me change this for a second. Okay. Right now, what I'm plotting is the original one, test. So I'm plotting test. So it's okay. It's okay. It's not normally distributed. But now let's plot L test, which is the logarithm of our log normal distributed data. So I'm just changing this line. I'm plotting now with respect to L test, and voila, we can see that is very much on a straight line. So our conclusion from this analysis is that after applying the natural log to our data, the data is normally distributed, meaning the original data was log normally distributed. And that's it. So I will leave this IPython notebook so you can play with it. Thank you.